All right, so in that first part of this activity, you were introduced to this dy dx. All right, now what that did on your calculator when you chose that function is that allowed you to find the slope at a particular point. Now we started with a straight line, and the next section will go on to a curved line, and you'll start to be able to see how this is even more useful. All right, but I want to talk a little bit about why dy dx gives you the slope. All right, so the dy dx is just a shortened or slightly different form of this delta y over delta x. All right, now delta y over delta x, that should look somewhat familiar because the change in y, delta y, is y2 minus y1, and the change in x is x final minus x initial, right? So these are just the change in y is final y minus initial y, and same thing for x, all right? So when we say dy dx, what we're really finding is the gradient. And we'll talk about this a little bit more, okay? But one of the things I want you to recognize is that, we've been talking about slope, okay? And this may be the word that you're familiar with. We started using the word gradient more commonly in this unit. This year when we were talking about tangents and normals and things like that. So I want you to get comfortable with the word gradient because that's the word IB will use. They're not going to use the word slope. Okay. Other than that, there's not a lot more that I wanted to show you here. It's just getting used to that idea of the dy dx. Now there are a couple of different ways that this type of thing is noted. Instead of dy dx, sometimes, so I'm going to write down a couple of ways that this can be. Sometimes they just write down this, y prime. And if you see that apostrophe after the y, it's kind of like the naught from probability, but instead this is the derivative of the function or the gradient of the function. You can also see it written sometimes this way. You'll see f of x and they'll throw the prime in there, just like that. Okay. There's other situations where if we're talking about, instead of talking about y and x, maybe we have a function where volume is dependent on time, right? And so you might see something like this, dv dt. And when you see that, the v is your y value and the t is the x value. So the volume depends on time, like how much water is in a bathtub or something like that. All right, so this is just a quick introduction. I'd like for you to go ahead, once you finish this, to move on to part 2, which is extrapolating this idea to curves.